Hi students, in this video lecture we will go through membrane reactors, right? Membrane reactor, we will look into where these membrane reactors are used, right? And then we'll see some important types of membrane reactors, right? Mainly two types of reactors depending on the catalyst. And then we'll do some mole balance, right, on the reactants inside the membrane reactor, right? So membrane reactor, as the name says, any reactor configuration, right, that contains a membrane inside it is a membrane reactor, right? So simple, reactors that contain membrane are your membrane reactors. Now you know what is a membrane, right? Membrane, we have done this in physical chemistry while doing osmosis, right? Reverse osmosis, desalination of water, right? So membrane has small pores in it, right? And the pores are of specific size. Based on the pore size, the membrane will allow particles of only specific size to pass through it, right? So we call it a semi-permeable membrane. It will not allow everything to pass through it, but it will only allow particles of specific size to pass through it depending on the pore size of the membrane, right? And membrane reactors, so let's just write first reactor configurations. Reactor configurations containing membrane, right, are your membrane reactors, right? And we know what is a membrane, we have just discussed. Applications where these membrane reactors are used. Membrane reactors are specifically used in thermodynamically limited reactions, right? Now what are thermodynamically limited reactions? Those reactions that are reversible reactions and at equilibrium, right? The equilibrium lies to the reactant side, that is towards the left, right? And the second example of thermodynamically limited reactions is your dehydrogenation, right? And the second type of reactions are your multiple reactions. In multiple reactions, membrane reactor is used to improve the selectivity, right? Selectivity means where you have more than one type of reaction occurring, right? But one is the desired reaction, the other reaction is not the desired reaction. So you will use membrane reactor in order to inhibit or stop the other reaction, right? We will be discussing the first thermodynamically limited reactions more in this, right? Then in other chapter, in multiple reactions, there is chapter multiple reactions in chemical reaction engineering. There we will discuss about use of membrane reactors in increasing the selectivity of multiple reactions, right? So these are used, right? Membrane reactors are mainly used first in thermodynamically limited reactions, right? That means where equilibrium lies to the left, that is, to the left means towards the reactant side. Second type of reactions, to increase selectivity in multiple reactions. Example of first type of reaction is dehydrogenation that we will be discussing in this lecture, and the example of second type of reactions are partial oxidation of hydrocarbons, right? Then you have nitration, right? There are some more type of reactions where you have multiple reactions occurring, and we use membrane reactor to increase the selectivity, right? And so basically let's discuss the first type of reaction, thermodynamically reversible reactions. Right, suppose this is the reaction, right, B plus C. These are your products, right, but the desired product is B, right, your desired product is B. Now what B is doing, B is reacting with C to give you back reactant A at equilibrium, right. That means this reaction, in this reaction the conversion is low, right. That means the conversion of A reactant into B product is low. Why? Because B and C are reacting and they are giving you back this reactant, right. And there are many reactions where this situation can occur. So what you do is you do these types of reactions in membrane reactors that contain membranes, right. So what membrane reactor will do, as we said, that a membrane contains pores, right, and they will only allow pores of specific size to they will only allow particles of specific size to pass through it, right. So in this case what we can do is to just without the membrane reactor, just think, if you want to improve, right, the conversion of this reaction, what you can do is, if you remove, suppose this is the main reactor product, right, because this product is reacting with the second product to give you back reactant. If somehow you will remove this product, right, if somehow you remove this product, right, B has nothing to react now to give you back A, right. So what you do is, in membrane reactor you remove one of the products, right. How you do that? You have a reactor, say this is your reactor, right. Now it has a membrane inside, right. Here is your feed, right. It forms B plus C, right. Now if this is your membrane, right, now this can pass out, this product can pass out through the reactor. You have a membrane, right. Now suppose inside the reactor where products are getting formed, right, and inside the reactor only B and C will react to give you back A, right. Now suppose you have a membrane inside and you want to remove the second product C. What you will do is, you will put a membrane in this reactor. Now the particles, the pore size of this membrane is such that only C can pass through it, right. The C, the second product, will pass through it, right, and through this membrane it will pass out, right, because this reactor contains a membrane and this membrane will only allow C to pass through it, right. So C will, the moment C will form, this membrane will let C to permeate, right. It will allow C to pass through it, and through membrane it will go outside the reactor, right. It is removed from the reaction. Now what is left is B, right. So using this membrane you have removed C, now you have B, right. Now B have no C because C has already passed through this reactor, C has already passed through this membrane out of the reactor, right. Now you don't have C, that will react will be to give you A, right. So now the equilibrium will not lie towards the reactant side, towards product, it will lie towards the reactant side only, right. So it would be like this, B plus C. Here I made this arrow bigger because the reaction is thermodynamically limited and it lies on the reactant side towards the reactant, right. I hope this concept is clear. This is the concept that is used in your membrane reactors, right. I hope this is clear. Now you have two types of membrane reactors, right. Now this reaction may contain a catalyst also, right. Now depending on the catalyst, you have two types of membrane reactors. There can be a reactor that contains catalyst with the feed, that means with the reactants. So catalyst with the feed, and what is feed? We know reactant, right? So we call this type of reactor where membrane reactor where you have catalyst along with the feed, that is you have catalyst may basically on the feed side, right? If this is your reactor, right, and this is your say membrane, right, and here you are passing your feed, right, here you have feed, right, along with this feed say you have catalyst particles also inside, right? So here you have feed along with the reactants only, right? Your catalyst is with the reactant only, is with the feed, right? So we say that catalyst is on the feed side, right? So we call these types of reactant as we give it a name as, we call it as inert membrane, right? Inert membrane feed reactor, right? Inert membrane reactor, right? Inert membrane reactor with catalyst, let's say pellets on the feed side, right? We call it as IMRCF, right? This is how we abbreviate it, right? And just look at the word inert membrane, right? Why we are calling it as inert, you will understand it once we look at the second type of membrane reactor, right? So this is the first type of reactor where you have catalyst along with the feed, or the catalyst on the reactant side. That is why we call it as catalyst pellets on the feed side. Feed is your reactant side. Second type of reactor, and this is your membrane, remember, this is your membrane, right? Now second type of reactor where the catalyst is deposited on the membrane, right? You have reactants here, feed, right? Reactants are inside, whereas the membrane on the membrane the catalyst is deposited, the second type of reactor, right? So on this membrane only the catalyst is deposited, right? I hope this is clear. We call this as catalyst membrane reactor, right? This is your catalyst membrane reactor. I hope this is clear, right? Now let's take one example. Example is C6H12, right? This is a dehydrogenation reaction. It will form C6H6 plus 3 hydrogen. Dehydrogenation reactions, that means where hydrogen is getting removed. This is your reactant, these two are products, right? Now this reaction we say is a thermodynamically limited reaction, where we have already discussed that your equilibrium will lie towards left, right? So here C6H6 and hydrogen will react to give you back C6H12, right? So now how can we increase the conversion, right? That means how can we increase the conversion of C6H12 to C6H6, right? We say the answer is by using a membrane reactor. What membrane reactor will do? as we have discussed here, it will remove hydrogen through the membrane, right? It will remove hydrogen through the membrane, right? Due to which the conversion of C6H12 into C6H6 will increase, right? So this is the basic engineering behind your membrane reactors, right? So just understand, whenever in practical situation, wherever you see a membrane reactor, right, just understand that these are the two main things where membrane reactors are used, right? And in such dehydrogenation reactions, one of the reaction product will pass through the membrane and is removed, right, from the reactor basically. When you don't have, say, hydrogen in the reactor, there is nothing to react with benzene to give you back C6H12, right? I hope this is clear. So this reaction, if carried out in this type of a reactor, hydrogen will diffuse out. This hydrogen will diffuse out, right? Say this is your hydrogen and this is your C6H6, right? And C6H12, right? That is reacting to give you C6H6 and hydrogen. Because this is a thermodynamically limited reaction, right? And your equilibrium lies towards left, right? So you will remove hydrogen using the membrane, right? Because the particle size, the size of hydrogen is very small compared to C6H6, right? So membrane will allow only hydrogen to pass through it. It will not allow C6H6 or C6H12 to pass through it, right? Basically here you have, in the reaction mixture, you have C6H12, C6H6 and hydrogen, right? And this membrane will allow only hydrogen to pass through it out of the reactor, right? So when hydrogen will remove from the reactor through the membrane, there is nothing to react with C6H6 to give you back C6H12. This is how we will carry out thermodynamically limited reaction in membrane reactors, right? To increase the conversion, right? Basically. So basically we use membrane reactor in thermodynamically reversible reactions to increase the conversion, right? So basically this is to increase the conversion, right? And in the second type of reaction, to increase the selectivity. Just remember these two things, right? I hope this is clear. Now we'll just do a mole balance, right, on the reactants and products that are inside. We will take it in this form: A plus B plus C, right? Now when we will do mole balance, just remember what we did in tubular reactors. Mole balance in tubular reactors, right? We have done this lecture before, so I just put a link here at this point, right? You can click that and you can go to how to do mole balance there, right, in order to understand this, right? So let's quickly do mole balance, right? So when we will do mole balance, we will not take the catalyst weight, right? We will take the reactor volume, right? In mole balance we will do reactor volumes, right? So say you have in the reaction mixture, right, you have reactants and products, right? So you will have A, you will have B, and C will get removed using membrane, right? So when you will do mole balance on A, right, we are doing this using what we did, the way we did mole balance in your tubular reactors, right? And we will be doing this in volume delta V, right? So when we will do mole balance on reactant A, right, when we will do on reactant A, what we will get? We will get dFA upon dV is equals to RA, right? Similarly on reactant B, we get dFB upon dV RB. Right? I again advise you to look at the tubular reactors, right, in the previous lecture that we have done, if you have any confusion with this, right, because I cannot do all along, because this lecture will go very long in that case. Right? Now, important thing is on this is your product, this is not your reactor. When we will do it on product C, which is passing out of the reactor. Right, now let's see. In mole balance, what we used to do is in by flow minus out by flow. Right, this is how we used to do it. Right, now in this case, out by diffusion. Right, because this product C is getting removed through this membrane via diffusion. So we will say out by diffusion, and out. Out is when it is coming out of the reactor normally. Right? In minus out by diffusion plus generation. I hope you remember mole balance equation is equals to accumulation. Right? This was the mole balance equation. Right, we are doing this mole balance over differential volume dV. Right, if you remember, we used to do this, right, we considered this much volume, right, delta V, right, this is V and this is V plus delta V. Right, if you remember, this is how we did. Now this is your FCV, right, minus out FC by V plus delta V. Right, when we consider this, here it will, we are considering delta V. Right, so FCV, right, FV is what entered here at V. Right, FCV plus delta V is what came out from here. Right, and out by diffusion. Right, what is going out through the membrane? Right, that would be, we take it as RB delta V. Right, RB delta V. Plus you have generation is, we are taking it as RC delta V. Accumulation is 0. On C, accumulation is 0. Right, I hope this much is clear. Right, why accumulation is 0? Because it is getting removed. C is getting removed. Right, now this is RC delta V. Right, and if you recall, right, we used to apply the limit formula. Right, limit formula was FC V plus delta V. Right, I take this there, simple maths, FCV, right, is equals to RC delta V plus RC delta V. Right, now you divide both sides by delta V. Right, so what you will get, FC V plus delta V minus FC V delta V is equals to RC plus RC. Right, I hope till this point it is clear. Let me just rub this off. Right, now here you have the limit formula. right? Now if delta V tends towards 0, right, and taking limit, what you will get is, if you take limit of this and delta V tends towards 0, what you will get? You will get dC upon dV is equals to RC plus RC. This is mole balance for your product that is leaving through the membrane reactor, leaving through the membrane, sorry, right? You can further calculate RC, small rc and capital RC, right? But right now we are not doing that, right? So your RC is your molar rate of B, sorry, capital RC is your molar rate of C leaving through the reactor, right, or leaving through the sides of the reactor, that is through the membrane, right? I hope this is clear, right? Just remember mole balance, and you can check tubular reactor for if you don't understand mole balance, if you have any doubts on it, right? I hope this is clear. So in membrane reactors, just remember membrane reactors used for thermodynamically limited reactions to increase the selectivity in multiple reactions, right? And types of thermodynamically limited reactions, right, where you have catalyst deposited on the membrane, right, catalytic membrane reactor, and where you have catalyst on the feed side, right, inert membrane reactor where you have catalyst pellets on the feed side, right? Then what we did is we took one example, right, how membrane can help us to improve the conversion, to increase the conversion, because this is mainly, membrane reactor is mainly used to increase conversion in thermodynamically limited reactions, right? So C6H12 gives you C6H6 and your hydrogen. Hydrogen are small molecules, can be removed through membrane if you carry out this reaction in your membrane reactor, right? Then we did mole balance like this, you got this, right? I hope this is clear. Now in next lecture we will be looking into other types of reactors. Thanks.